It's me, Kusum, right? Uh, and today we're going to discuss regarding the course title Algebra, and somehow today regarding this algebra, I think already I displayed in this screen our title today, and today we are going to discuss regarding this subgroup definition. So we'll try to define subgroup along with some example of the subgroups, and mainly we'll focus today on this Lagrange theorem and how can we prove and how can we show the proof of this and how it is possible by easier way to understand this Lagrange theorem behind this session today. Okay. Subgroup definition, I try here to define at first. Let G be a group. A non-empty subset S of G is a subgroup of G if S itself is a group under the binary operation defined on G. That means actually what we define, how we define the G group. So by the similar operation and by the similar condition that S must be satisfied. That means S should follow all the operations whatever we did in G. Okay, more precisely, if S contains the identity element of G and every element of S has inverse in itself, then S is a subgroup. So let's say that identity element on G, that identity element, same element should contain in S2. So S itself has the inverse in its subgroup or the group. So that is S itself is a group. For S to be a subgroup, it must satisfy some conditions over here, like in the group. So here first closure. So if A and B belongs to in H, the operation between them should, or operation of A and B should also belongs, or that their output should also belongs to H. That is the closure property. In this way, next identity, the identity element E, whatever belongs to in G also should in H. Likewise, inverses. If the A belongs to in H, then obviously the inverse of A must belong to H. Okay, so these are the some, that means properties also of group. Okay, let's go for the next. Okay, now some examples I have mentioned here. So by taking the integer under addition, so Z is the symbol which can be expressed as a integer under the addition operation is a subgroup of the real R under addition. In this way, any set which contains only identity element of a group G is also a subgroup of G, and G is also a subgroup of itself. Means if identity element is there, the G, that is also the what subgroup of the G, as well as G itself is also the subgroup of G. These subgroups are called trivial subgroup. So every group G has the trivial subgroup, that is the set of the E, that is E means identity element. So while doing operation with the identity element in a group, that never makes any changes to other elements after the operations in the output. Okay, the set of all even integers in a subgroup of Z with addition operation is also another example of subgroup behind this. Okay, for the next, now we're in the important session Lagrange theorem. So theorem, that's Lagrange stated like this. So the order of each subgroup of a finite group is a divisor of the group. It means if we are going to find subgroup from a group, then that order of the group must be divisible by the order of subgroup, otherwise we cannot say that is subgroup. Okay, so on the base of this, let's try to prove it now. So proof: let the G under the binary operation be a group of order n. We took any order number of that members in a group or the element in a group, say n. Okay, so that is the order of G is equal to n. Let S be a subgroup of G group. So then S is also finite. If so, then obviously from the finite group we're trying to create a new group as a subgroup. Obviously that must be the finite. In this way, let the order of S equal to m at this moment. Now let us consider that S1, S2, S3 dated up to Sm, because already we suppose that. So the order is m, so up to m element in this group are the m distinct members of S. For that's A belongs to G, we know very well that. So this A is the arbitrary element of G, where we can denote that An, that is A1, A2, A3, A4 like this. So and here by keeping one element or the arbitrary element, it means A means do the representation of the all the elements which are found in G. That is why, well, doing operation from by taking any element of G through the left side of this edge is a left coset of H in G, and we have the A binary operation to H subset equal to, we can create like this. We can show the A binary operation as 1 comma A binary operation to S2 comma S3 to so on up to A binary operation to Sm, means up to the last member or the element of this group. So we can show while doing this also what happens here. Actually we have to know that, so Si is not is equal to Ji, and I and J are the what, that means their place or the positions in behind this S set. Yeah, so they may not be the equal. Why? Because according to the set theory, there should not be the repetition of the same element in a set. Yeah, like in the group, that group also satisfy it, okay, or accept the set theory. Okay, so now, so here if so then well, doing the operations to this distinct element of the group by the same element of G as A by taking may not be the equal. So okay, so here also shown that the A binary operation with S1 is not is equal to A binary operation with J. For why? Because I is not is equal to the J over here. So thus the left coset, that means the A binary operation with S contains m distinct members. So I already told that means up to the n element, it is what that means it did operation by taking the different element from the G. That is why so orders remain the same over here. Now so if so, then we can write this order of the left coset of H by taking any arbitrary element of from the what, any one element from the G, also the equal with the what, this OS. So order of S here we can say, that is why it is also equal with n. Now let's proceed is, so since the left coset of S in G are either disjoint or the identical, also G is a finite group, so number of distinct left cosets of S in G will be finite, say equal to k. Now if so all are finite, then obviously it also will be the finite. So let's take as a finite number k for this. Also we know that the union of sets distinct left coset of S in G is equal to the G. So while talking regarding this, so I like to say that 1, 2 and 3 are the set. Suppose this set we can say that it is S. So in this way, union of another, that means suppose it is 1, 2, 3 and dot, 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 up to 10. Suppose 10 is already what is k. Now it is, let's say it is like a G, then obviously the what union of them is all what is must be the G, because this all 1 2 3 is on inside here. So according to this, let's try to understand this part also. Okay, so let's see now. So as we know that, so here G is equal to, now all that means by taking a1 element from the G, let's do the operation with the element of S. This is the what uppercase letter S is written. It means the what subgroup, group is denoted by the capital letter. So behind this, yeah, many elements are there, like S1, S2, S3 we discussed before. Like here also A2, while taking the A2, with the A2 also we did the operation of the distinct element behind this subgroup S, so on up to by taking the last element of the G, also we took again here did the what operation with the S. So we got here like this. Suppose S1 A1 S, that provides the what M1, sorry what is M element, or that means an M order is there, like previously we did discuss also, is it? So here in this way, here next previously what we discussed is here. Okay, so here actually the order of S is equal to what was here, there was M, yeah. So order of S, in this way order of the what that left coset, so AS also similarly we got the what M. In this way here A1 is there in S, that also provides the what is M. Here this also provides the M, because up to the M distinct elements were there in the S. This this helps to what according to the base of this S, that elements order of elements will be defined here. In this way this also provides the what is M up to k times. That is why suppose here we have written that is 2 plus 2 plus, yeah, simply 2, then what can you write 3 times, no, 3 times 2, like this. Here k times, so k times m's are there, so k times m is written here. In this way, that is k times m, k time is already k means k, m is what is, m means what is order of S, what we discussed, yeah. M is what is order of S, we already discussed. Okay, in this way let's keep the value now. Thus, so order of here, order of OG, that means order of G is equal to k times of order of S is means, yeah. So while dividing this one, suppose while dividing this one with the order of the S, then this may be the what divisible, right? So there is the k times only. So but let's not divide directly like this. It means we came to know that order of G divided by order of S, that is n number of orders are there in the G, and m times of orders are there, m number of orders are there in the S, so these are divisible each other. So I think it became clear, so hope I made you understand. Thank you very much.